Okay, so the topic for this video is enzyme regulation. Now, before we get into the specific mechanisms of how enzymes are regulated, what we need to discuss is and understand is why enzymes are regulated. And I'd like to take an illustration from the Mark's Medical Biochemistry book that I've recommended in class, because this is a very nice illustration he has. And it has to do thinking about a freeway. So if we have a typical multi-lane freeway, what we have are cars progressing down the road at their normal speed. So what we could consider this freeway is a metabolic pathway. So recall in class we discussed that biochemistry is about pathways. We talked about single reactions where we have substrate A forming product B, but then biochemistry is largely involved in these combining these reactions in pathways. So substrate A becomes product B, but then product B is a substrate to make product C. Likewise, product C becomes substrate for the next reaction to become product D. Product D then becomes the substrate for the subsequent reaction to form product E. And of course, each one of these reactions is mediated by a separate enzyme. And I will abbreviate these by E1, E2, E3, and E4. Now, the freeway analogy here is the pathway. So this is going from A to B to C to D to E, etc. Now, what's important in regulation is that sometimes we need to take an alternative path. For example, we may need to take product C of this reaction from enzyme E2 and turn that into a substrate, not to form D, but to form, say, for example, D prime. This might be done by enzyme X. Now the question becomes this direction versus this direction, the direction from C to D or C to D prime. This is what I like to call a decision point. And a decision point simply means that we have the possibility of a substrate becoming two products. So what dictates this? Typically, we are going to be using our principle of thermodynamics to determine this. Recall our thermodynamics, change in free energy equals the change in the standard free energy plus the natural log of our product over substrate. What we are going to be changing here is the substrate-product relationship in order to alter the thermodynamics to make this decision point. So how does that occur? Let's look at our freeway again. These cars indicate the substrate and products moving down the road. Now what if we put a barrier in the middle of the freeway, say a construction zone? What's going to happen is everything behind this barrier, all these cars behind the barrier, are going to slow down because all of these cars in the right lane need to move to the left. That is going to slow the progress of this reaction. Think of this as increasing the substrate concentration behind the barrier. Now what that will allow us to do is cars coming this way will have a choice. Because this area is building up, they can take an off-ramp and take an alternative course. Now what does that mean here in terms of our pathways and thermodynamics? Well, let's say, for example, that A is forming B, B is the substrate for E2 and forming product C, so we are progressing down our pathway. But now when we get to this point here, let's say that C, instead of becoming D, let's say that we are able to inhibit enzyme E3. Inhibit means regulation. So this is a down regulation event. If that occurs, the conversion of C, substrate C, into product D is going to slow. That means that under these conditions, our concentration of substrate C is going to increase. Now typically in biochemical reactions we could have this potentially reverse, because now this being the product of this reaction starts to increase, and now we have an increase in P over S, and now we have a positive large number here, and so we can move in the other direction. But what we want to do is move into this direction, because this is our branch and our pathway, our decision point. So if enzyme E3 is inhibited, let's say that thermodynamically this is very difficult to go backwards, because the concentration of B is also increasing, because remember E1 is continually converting A to B. So that means that this is not going to be low enough to drive this reaction backwards if concentration of C is increasing because of the block on E3. What about D prime being our product? Well, this branch point has not been used up to this point. We have only used the main pathway. So that means the concentration of D prime is very, very low. We inhibit E3, building up the concentration of C, substrate, and now we have a very large difference between this substrate C and our product D prime. That means if we make pre-D prime substrate C, this is going to be a negative number, a large negative number multiplied by the gas constant and temperature, offsetting the standard free energy, making this a negative delta G in the alternative direction. So this is one of the most important properties of enzyme regulation, is that we are able to take branch points at these decision points and fill these branch pathways, diverting substrates and products from the main pathway into branch pathways by inhibiting downstream enzymes. Now let's take a look at the types of regulation. The first one we want to take a look at is what's called an irreversible inhibitor. So an irreversible inhibitor is one of our simplest mechanisms of regulating enzymes. Recall our enzyme plus substrate forming our enzyme substrate complex. Then this can form our enzyme product, and then of course these can dissociate, forming enzyme product separated. What a suicide inhibitor is going to do is it's going to form an EI complex. So we are going to add the enzyme plus the irreversible inhibitor. This is going to form the EI complex. Now what happens at the EI complex is that this reaction gets stuck. because there is no reversing this reaction. It further gets stuck because there is no catalytic activity to forming the E product reaction, so this reaction is blocked. So a suicide inhibitor essentially traps the enzyme into the intermediate enzyme substrate, in this case enzyme inhibitor complex. The only way to resolve this is to make new enzyme through biosynthesis. Okay, the next type of inhibitor is called a competitive inhibitor. Now, a competitive inhibitor is exactly what it's described as. If we have an enzyme with an active site, we typically have a substrate, of course, that will fit into this active site reversibly. And in doing so, we are going to form an enzyme substrate complex. This, of course, will go on to form enzyme product. What a competitive inhibitor is it's an entity that is going to compete with the substrate. Because the shape of the inhibitor is the same as the shape of the substrate. Typically, these are reversible. The binding of the end of the inhibitor to the substrate, to the enzyme. If this was not a reversible reaction, then it would be an irreversible inhibitor because it's trapping in the ES complex. But because it's reversible, this means that the substrate can also have access to that active site. Now, once we form our enzyme inhibitor complex, there is no further reaction because the inhibitor resembles the substrate to fit in the active site. However, notice how I've drawn the inhibitor, that it prevents the catalytic reaction of converting this molecule into anything else. So what it does is it displaces the substrate, and so the substrate cannot be converted to product. Now, what does this look like on a graph? If we measure our VO to substrate concentration to develop our kinetics on this enzyme, with enzyme and substrate, we see our typical hyperbolic reaction, hyperbolic curve. Here is our Vmax. Here is our 1/2 Vmax, and recall the definition of Km as the substrate concentration that gives 1/2 Vmax. Now, if we do the same experiment, mixing the enzyme and substrate concentration, but now we also add inhibitor, what we're going to get is a slightly different curve. This curve is plus inhibitor. Now notice that eventually here, with the inhibitors as a single concentration inhibitor, if you add enough substrate, you can outcompete the inhibitor from binding to the active site and thus achieve Vmax. So with enough substrate, you will displace the inhibitor binding, its probability. With higher concentrations of substrate, the substrate has more opportunity to be occupied in that enzyme, so that the inhibitor now has no effect on overall enzyme activity, and then this can form product. Notice the shift in the curve. Now if we measure 1/2 Vmax plus inhibitor, we have now a new Km. And it shows that the Km is higher. This is actually called a Km apparent. So the Km appears higher for the enzyme and substrate in the presence of inhibitor. The question is does the enzyme substrate actually change affinity in the presence of the inhibitor? And the answer is no. The enzyme and substrate affinity is the same whether it's without inhibitor or with inhibitor. But the very presence of the inhibitor makes it look like the affinity is lower because it is now displaced substrate. It takes a higher concentration of substrate to reach 1/2 Vmax, not because of a reduced affinity for the enzyme, but simply because the presence of the inhibitor, which is competing for that active site. Now if we draw our Lineweaver-Burke double reciprocal plot, where we have our 1 over concentration of substrate, 1 over VO, what we will have is our line without inhibitor. So this is minus inhibitor representing the top curve here. And of course this is the negative 1 over the Km. This point here represents 1 over Vmax. Now if we do a double reciprocal plot on the curve here with inhibitor, this is going to look a little differently. Notice that with inhibitor, at high concentrations of substrate, we have no change in Vmax. So that means that the Vmax is the same of the enzyme. The maximum velocity of the enzyme is the same whether you have substrate or inhibitor. So that means that point will be the intersection. But notice the Km with inhibitor is higher now. So a higher Km is going to shift this curve to the right towards 0. This will be plus inhibitor. And so now this is our negative 1 over Km apparent. Recall also that the slope of these lines is Km over Vmax. So if we look at the slopes of these lines, we'll see that the Vmax is the same for both, but the Km is higher for with inhibitor than it is without inhibitor, and so this means that with inhibitor we will have a greater slope, confirming our line. So now the next type of inhibitor we have to look at is called a non-competitive inhibitor. So what does a non-competitive inhibitor look like? Let's draw our enzyme again. Here is our substrate, shaped to fit into the active site. Of course, this is reversible enzyme. Now, what a non-competitive inhibitor is going to do is it's going to adjust and affect the enzyme activity without competing for the substrate. So what that typically means is that now there is what's called an allosteric site. On the enzyme. The allosteric site is a regulatory site that is present on the enzyme that is not the active site. So our inhibitor now will bind specifically to this other site. This, of course, is going to affect the enzyme activity. So if we look at our velocity versus substrate concentration graph, without inhibitor, we will see this. Minus inhibitor. Again, here is our Vmax. Here is our 1/2 Vmax. And of course our Km for this enzyme substrate. Now if we measure the kinetics of the enzyme in the presence of substrate and now have enzyme inhibitor present, what we will achieve is something like this. This being plus inhibitor. Now notice that we now have a new Vmax. 1/2 Vmax for this reaction is the same Km. So what this kinetic graph is telling you about this inhibitor is that in the presence of the enzyme activity, the maximal velocity of the enzyme possible, is being reduced because the inhibitor is slowing the enzyme. It's regulating it. It's negatively regulating. However, the Km of the enzyme substrate is not changing because there's no competition for the enzyme to bind the substrate. The inhibitor does not compete. It is not a competitive inhibitor for the substrate. The inhibitor binds an allosteric site. So under these conditions, with non-competitive inhibition, let's draw our Lineweaver-Burke plot. This, of course, is minus inhibitor, our control. Here is our 1/Vmax. We're graphing, of course, 1/VO versus 1/substrate concentration. Here is our negative 1/Km. And now, with the inhibitor, notice that the Km is not changing because this is a non-competitive inhibitor. So that means we are going to intersect this point with inhibitor, but our Vmax is getting smaller. So if our Vmax is getting smaller, that means it's going to be a bigger number. So this curve, this line, would be plus inhibitor. And then this would be the 1/Vmax for the inhibitor present. If we examine the slopes of these lines, again, Km/Vmax, what we notice is the Km is not changing. So the numerator for both of these lines is the same. But Vmax is changing. So Vmax is decreasing with the inhibitor. If the denominator decreases, that makes the slope greater, confirming our line. Now another type of enzyme regulation is what's called a covalent modification. And a covalent modification is simply adding a different chemical group to the enzyme in a way that it forms a covalent bond and it regulates the enzyme activity. So a good example here is that if we have an enzyme and we need to regulate this enzyme, so let's say that we want to decrease activity, what we can do is add a phosphate group. Now adding phosphate groups, we're typically going to be using ATP, and we are going to be using one of the phosphates of adenosine triphosphate to make adenosine diphosphate, and then this enzyme will be covalently bound to a phosphate group. This presence of the phosphate on the enzyme alters the conformation typically of the enzyme and decreases its enzymatic activity. Now the general class of enzymes that do this is a separate enzyme, are kinases. So a kinase enzyme will take ATP, use the energy of ATP, and transfer one of those high energy phosphates to an enzyme to regulate it. In this case, the covalent modification with the phosphate decreases activity. In some cases, it can increase activity. Now the reverse reaction, let me correct these arrows. The reverse reaction can also occur. So if you want to increase activity of the enzyme, you will remove the phosphate from the enzyme, restoring its activity. These enzymes are called phosphatases. We'll get into specifics of phosphatases and kinases. But this is a covalent modification. Now there's one more type of regulation, and this concerns a different type of enzyme structure. This is a multi-subunit enzyme. So recall in our protein structure, this is a protein that has quaternary structure. So it is not a single enzyme subunit, not a single polypeptide, but multiple polypeptides that come together to form quaternary structure. Now, because of the multi-subunit enzyme nature, this does not follow Michaelis-Menten kinetics. So everything that we've looked at in our previous graphs, with our graphs of velocity and substrate concentration, and then doing our transformation into Lineweaver-Burke, none of this applies on a multi-subunit enzyme. And the reason for that is because of cooperativity. Because there are multi-subunits together, let's say, for example, these two are subunits. This has the active site in it. This is the regulatory enzyme. This enzyme could have a specific affinity for the substrate, which would be binding to the enzyme. But then we also have another subunit here that could affect this activity in a positive or negative way. So maybe this subunit increases the inherent activity of substrate for this enzyme. So then it affects the affinity of this enzyme, and then we have two apparent affinities. So the way these graphs tend to look, we can still graph our equation of velocity versus substrate concentration, but this graph will look sigmoidal. This is still considered a Vmax, and we can still consider this Km. Not really, because it doesn't follow the true Michaelis-Menten kinetics. However, it is a measure of affinity of enzyme and substrate. It's just not properly classified as Vm, as Km. Now, how do we regulate these enzymes? If we add an inhibitor, this of course is minus inhibitor, these enzymes tend to look like this. This is plus inhibitor. Notice what we've done. We've shifted this curve to the right. So that means it's going to take more substrate to achieve the same level of velocity. The other way to look at it is if this is the same amount of substrate that gave this much activity, now the same amount of substrate gives a much lower amount of activity. It's been inhibited. Alternatively, we can also add an activator. Perhaps we want to increase the enzyme's activity. So now this will shift the curve to the left. Likewise, for the same amount of substrate, notice the increase in velocity of the reaction. This occurs on a multi-subunit enzyme, and this is called, generally it's called allosteric regulation. Again, this does not follow Michaelis-Menten kinetics, so this is not a measure of Km, but it is a measure of affinity. And we have multiple slopes indicating cooperativity. So at low substrate concentrations, notice that we have a very low slope. That means weak activity of the enzyme, but as we increase substrate concentration, now we exponentially arise the velocity of the reaction, indicating a positive cooperativity here. We'll get into more of this reactions when we talk about hemoglobin.